All right, so here we go with some worksheet help. This is the acid-base conjugate pair, acid-base strength of conjugate pairs. I got a call coming in. I'm going to mute. I'm going to go on. So, there were some questions they said on page 206. Everything's filled in there. So, while we're online here, if you have a specific question on page 206, let me know, because everything's filled in there on the answer key. So I'm going to go to 208, and if while we're on the line here in the session,
Number 9 and 10 on page 206.
Number 9 and 10. Chloride ion. So the chloride ion, whether it comes from HCl or KCl, in solution, let's do it this way. So whether it's hydrochloric acid in the presence of water or potassium chloride in the presence of water, these are strong ionic, so they completely dissociate. So the hydrogen is going to join with the water and make H3O plus, and the chlorine is going to separate and be the anion. So HCl is a very strong acid, and so when it dissociates, this being a very strong acid, when it dissociates, its partner is what's left of it, and so this is the conjugate base, but it's weak. It's very weak. If this is very strong, this is very weak. And so when this Ka, like if you think about Ka values, Ka or Kb values, if the Ka value is 10 to the negative 7, and the Kb value is 10 to the negative 7, that's a pH of 7. So if this weak base is even less than this, it has even less of an impact on the pH than water does. So this is too weak. This anion is too weak to contribute to the pH change. What's contributing to the pH change is the hydrogen that came off to make hydronium. So anytime on the right-hand side you have hydronium, you know the pH of that is going to be acidic. If on the other side you have hydroxide, it's going to be basic. So we have a strong acid mixed with a weak base. Water it's amphoteric, so it's acting like a base here. And so because this is so weak, its Kb value is going to be less than 10 to the negative 7. It's going to have even less of an impact on pH than pure water has on pH. So it's the same thing here. It's the same thing with potassium chloride. The chlorine has no impact. And then number 10, same thing. So sodium bromide. Sodium bromide. The sodium came from sodium hydroxide, strong base. The bromine came from HBr, hydrobromic acid. This sodium came from a strong base. The bromine came from a strong acid, strong base. Mix them together and neutralize them. Your pH is going to be 7. And so it doesn't matter what the molarity is, the pH here is going to be 7. Because the bromine ion isn't going to have any effect on the pH from what we talked about above. The sodium ion isn't going to have any effect on the pH. The only thing that's going to affect the pH is the hydrogen combining with the hydroxide to make water. So if you think about these separating out, all you have in there is water, and water has a pH of 7. So, am I getting more questions on those?
Yeah, not on those two, but also the last problem on the back page, please.
Okay. I don't know about, I'll see about that one, but also I was asked about 208.
I don't have any specific numbers on that.
No, it's number 3. I mean, it's number 3 and 4, actually. So, I know number 3 and 4 weren't filled out. So, starting on page 207, number 3, it says, for each of the following, indicate whether the resulting solution will be acidic, basic, or neutral. If 1 mole were dissolved in 1 liter, provide the predominant, so forth. And it gives an example of sodium chloride. And then it says, recall what the strong acids are, hydrochloric, hydrobromic. So I'm on page 208, which is actually number 3A. So I'm going to do a couple of these. This is 3A. So this is NH4NO3. This is 3A from the acid-base conjugate strength packet. NH4NO3. Okay? So what we need to recognize here is that the NH4, we have to look at the cations and the anions. If we're asked whether this is acidic or basic or neutral, we need to see where they came from. So the strong bases, so the cation here is going to be connected to the base. So this came, we can either talk about this coming from NH4OH or coming from NH3. Either way, this came from a weak base. And this NO3 came from HNO3, and so that's a strong acid. So big picture here, weak base, strong acid, this is going to be acidic. All right. But the way, so if you think about this coming from a strong acid like HNO3, HNO3 is going to completely dissociate, and the anion here, the NO3 anion, again, this is a strong acid, so this is a very weak base, very weaker. It has a weaker Kb than water, so it has no impact. Okay, it has no impact. What's going to have the impact is the NH4, but overall, if this came from, I mean, just big picture, quick and dirty answer is if this is strong acid, weak base, it's going to be acidic because strong over weak. But it's the NH4 that we care about. Okay, the NH4 ion in the presence of water is going to be in equilibrium. So this is a weak base. What do bases do? They donate. So this is going to donate a hydrogen to become NH3. And it's going to donate it to the water, and the water is going to become the hydronium. So this is aqueous, this is liquid, this is aqueous, and aqueous. Now, just keeping like big picture here, again, I can just look at these species and say, where did this ion come from? It either came from NH4OH or it came from NH3. Either way, they're weak because you know that the strong bases are group 1, group 2 hydroxides. This is not group 1 or group 2 hydroxide. Then you look at the anion, you say, where did this side come from? It came from HNO3, which is a strong acid. So if you make strong acid weak base, you're going to get a acidic salt. And the chemistry of it, though, is because the nitrate doesn't have any impact, it's the NH4, it's the ammonium ion that does. The ammonium ion in water is going to produce your NH3 and your hydronium. Now, as soon as you see this over here on the right-hand side, as soon as you see hydronium, you know it's acidic. If over here we produced hydroxide, immediately you know it's basic. So, but this is acidic, and we can then do our, well, they had a Ka and Kb scenario. So you would actually look up the Kb value for NH4OH, or we could do, let's see here, so my K is going to be, yeah, so hydrofluoric. So I think we could look up the Kb value of NH4OH, Kb for NH4OH. You just look that up online or in the Master in Chemistry text. You get the Kb for NH4OH is, I had looked it up earlier, 1.8 times 10 to the minus 5. Okay, so you would look that up, and then you'd say, okay, so the Ka for this is going to be Kw over Kb, and Kw at room temperature is 10 to the negative 14, and Kb is 1.8 times 10 to the minus 5, and so Ka is 5.6 times 10 to the minus 10. This is your Ka. So that's how you would do one of those for A. So A is going to be weak base, strong acid overall, and acidic salt. It's going to be an acidic salt. Do we have any current questions?
This is number 6, but I don't know what page. I was going to ask, but
I can, yeah. But I want to continue with this, so before I get to that one. So then B,
number 6 on 208.
yeah. So B is, before we get to number 6, B is going to be cesium iodide, okay? So we're asking where, you know, we're looking at the cesium cation and the iodine anion. Okay, again, if we think about this coming from a base, this coming from an acid, so cesium hydroxide would be a strong base because cesium is in either group 1 or group 2, and iodine came from hydroiodic acid. And that's one of the that you need to memorize as one of the top 6 strongest. So this is strong acid. Right there, we can talk a lot about it. Like we can get real specific and write it all out. But the big picture here is strong base, strong acid. That's going to be a neutral salt. That's going to be neutral because a strong base is going to neutralize a strong acid. It's in general going to have a pH of 7. But then C is where we're going to have one the opposite of A. So for C we have CH3 COONA. So what we're recognizing here is we have the two parts. This part here, this is reversed because normally we would have the sodium on the front end. For some reason they put it on the back end. You could see it either way. So of course you have to recognize that sodium is a positive ion. So this is your cation and this is your anion. So it is absolutely your job to recognize that this sodium if it's a cation, it used to be attached to a base. So sodium hydroxide. Sodium is group 1, sodium hydroxide. This came from a strong base. CH3COO is the acetate ion from acetic acid. And so this wouldn't be just in a non-context. Like in the stem of this question, you would have seen acetic acid, which is H2 HC2H3O2. You would have seen acetic acid like this, or you would have been told this is the acetate ion. But definitely you're recognizing that this CH3COO is the acetate ion, which came from acetic acid. And because you memorized what the 6 strong are, you realize that acetic acid is weak. Okay, so this is the anion of a weak acid, all right? So like A, we had strong acid, weak base, it's going to be an acidic salt. Weak acid, strong base, this is going to be a basic salt. But the chemistry here, again, now, this sodium ion came from a strong base. So that means the sodium that splits out of that is a very, very, very weak conjugate acid, which means it doesn't have any impact on the pH. The anion here does, okay? And so we're going to write this out as this anion, the acetate ion, okay, mixed with water, is going, so this ion came from, like, the whole thing. Let me write this out here. Okay? The whole thing is a weak acid. All right? So over on the other side, we're going to have the hydrogen and the CH3COO ion. This was the weak acid, which means this is the base. This is the conjugate base. If this is the conjugate base, it is going to accept a proton from the water. So we're going to get our HCH3COO.
We actually can't see that bottom. The glare from the window, yeah.
Okay. Can we see up here?
Yeah.
Right here. And OH. So it's a little difficult because I'm still new at doing this through a camera instead of having you live, so you can ask questions and I can see your faces and whatnot. But what I'm trying to help you see is that when you see something like this and you're asked, is it acidic, basic, or neutral, you're deciding where these things came from. And so you need to be able to recognize that this is the acetate ion. And acetate came from acetic acid. And acetic acid originally, when it produces the acetate ion on the other side is the conjugate base of the acetic acid. So if this is a base in water, the water is going to act like the acid. It's amphoteric. And if this is the base, it's going to take a hydrogen. So now what do we have over here? Acetic acid. We have acetic acid and hydroxide. Now this is what I said at the beginning. When you're doing these, if you see hydronium over here, H3O+, you know that's going to be acidic. But if you see hydroxide over here, you know that's going to be basic. All right, it's going to be basic. So then we can do we can look up the Ka for we can look up the Ka for acetic acid and plug that in. So ultimately our Kb is going to be Kw over Ka. Can I not see this right here?
No.
So how about over here?
I can see that fine.
So ultimately we're looking at Kb is Kw over Ka. And we can look up the Ka for acetic acid. Kw, again, is 1 times 10 to the minus 14. Ka for this, again, is honestly, it's the opposite of, it's 1.8 times 10 to the negative 5 again. Now excuse me, I'm going to sneeze. So again, now our Kb is 5.6 times 10 to the negative 5. Now that's our Kb. Before, up here, it was our Ka, but now it's our Kb. Number 4 on that page asked to determine the pH of those. Okay? So I'm just going to do the pH of C here, of what we just did. So the pH here of this one, so C. So I'm going to erase some of this. And it says for a 1 molar solution of each. All right. So let me see if this is going to work here. 1, because we're actually gaining a hydrogen here. Yeah, that's right. 0, 0. That's right. That's going to work. So we're, well, so our, we subtract, that's, I think I'm going to do A instead to not make that confusing. So let me go back to A and do, this is going to be number 4A. So we have NH4 H4 plus H2O, the NH3 plus H3O plus, and if this is 1, initially this is 1 molar, this is 0, 0, then we're going to minus X plus X, equilibrium 1 minus X, X, and X. So our Ka is, we already figured out what our Ka was. It was 5.6 times 10 to the minus 10. And that's again going to equal X squared over 1 minus X. But again, if you look at your value of Ka, it's incredibly tiny. It's 10 to the negative 10. It's incredibly tiny. And so that means I can say X is negligible here. I can forget about it. So it's really 5.6 times 10 to the minus 10 equals X squared. So just take the square root of both sides. Of course, the square root of X squared is just X. And remember that X is your hydronium. And so take the square root of that, and you get 2.37 times 10 to the minus 5. And so that's your hydronium. And so the pH is the negative log of that. And that's going to be 4.63. So the answer to number 4A, determine the pH of all of them, is 4.63. So then for B and D, they would both be strong base, strong acid, strong base, strong acid. So those pHs would be 7. So what I would have you do, we can check them later, would be you would do C and E, find the pHs of C and E, and we can check those next session. Now, somebody else was asking about number 6. Now, are they still on, or can we tell if they're? The person who's asking for number 6, have you looked at the key? Have you looked at the?
Yeah, they're still here.
For the person asking about number 6, have you looked at the key and you don't understand the key? Or do you not have the key? Because I sent a worked out solution of that one. Crickets? Nobody's saying anything?
They don't understand the key.
Okay, so you've seen the key, you don't understand the key. Okay. Okay, so we want the, so we have a 0.15 molar KCN solution. All right. Here's what we need to recognize. And this is the challenging part of this. Understandably, this is the challenging part of this. You are to see that potassium is a group 1 metal, and any group 1 metal is soluble. So this is a salt. This is an ionic salt that's going to completely separate. And you need to see that this is going to separate into the potassium ion and the cyanide ion. And this would be a polyatomic ion that you would have memorized. Again, when it comes on an exam in May, they would give you more context and talk about the ion, or give or tell you, name the cyanide ion. But the first thing to do here is recognize that 0.15 mol, like if this is 0.15 molar, then this is 0.15 molar, and this is 0.15 molar, because it's 1 to 1 to 1. Now after that, you need to understand, where did this, like if this is a ionic salt, a a metal cation with a non-metal anion. That makes it a salt. Something from the left on the periodic table with something on the right, but in this case it's a polyatomic ion. You need to recognize where did this potassium come from? It came from KOH. And what's KOH? It's a strong base. If it's a strong base, when this splits out, the potassium has no impact on the pH. Only the OH is having an impact on the pH. So this has no impact, so I don't care about it. That doesn't have anything to do with the chemistry of it. What has to do with the chemistry of it is the cyanide ion. So Cn minus in the presence of water. So this is going to be aqueous in the presence of water. Is going to, so this is going to act as your, when, again, with water being amphoteric, okay, there is no hydrogen for this to give, right? This can't give a hydrogen. It doesn't have a hydrogen to give. This has a hydrogen to give. So this is going to take a hydrogen to become HCN. So if this took a hydrogen, what is it? It's a base. And this is its conjugate acid. And this is acting as an acid. And over here, what's left of the H2O after it gives a hydrogen? OH. And so this is your conjugate base. Okay? So then it's just a matter of an ice table, but we know that we're starting with 0.15. Our original here, we're starting with 0.15 because it came from up here. So this is 0.15 molar. We don't care what's happening with the water, it's a liquid, 0, 0. Our change is still going to be minus x. And this is plus x plus x. So our equilibrium is going to be, now it tells us what the Ka is. It tells us that the Ka for HCN is 6.2 times 10 to the minus 10. Okay? It tells us what that is. All right? But this is basic. This is a basic environment. So I want the Kb. Well, that's easy enough. If I have the Ka, I have the Kb. So Kb is equal to Kw over Ka. That's 10 to the negative 14 over 6.2 times 10 to the negative 10. You just plug it in your calculator. And so this is your Kb. This is Kb. You can plug it in now or you can plug it in later. So is this still a glare here?
Yeah.
So the Kb then, right? Well, let me just put it over here. So Kb is equal to Kw over Ka, so 10 to the negative 14 over 6.2 times 10 to the negative 10 equals x squared. X squared over 0.15 minus x. So I didn't keep writing that out, but my equilibrium would be 0.15 minus x. This would be x and x. So I have my x squared over, I have my products over my reactants. My reactants are 0.15 minus x. X is negligible. 0.15 is so huge compared to what my Kb is going to be. So I can forget about this x. So it's really equal to x squared over 0.15. So you would just do the math there. This is calculator work to get x. Well, what's x? OH. and that is equal to 1.6 10 to the minus 3. That's OH. It's asking for the pH. Well, the POH is going to be the negative log of this. And so then remember that pH plus POH equals 14. And so the POH is equal to 2.81. So the pH is 14 minus that, which is 11.19. So I'm not sure, because I can't see your face and I don't know who's asking. I don't know if that helped or not, but that was number 6. And I'm looking at the back page because somebody asked about the problem, because I have that worked out as well. For page 209, will the solution be acidic? So the person that's asking about number 9, do you not have the key or you don't understand the key? This is the last question on this packet. Okay. So I'm going to say that you can always ask me again about this last one, but I was just reading my key here, and I think I've got that answered. If you have more questions, though, I'm happy to talk it through, but I don't know if the person asking that is still on and still has a question. So I'm a little bit torn here. Like I'm imagining if you're sitting, at home watching this, I imagine you're finding it incredibly boring. But I don't know. I'm not going to spend the time to make it, do some kind of magic show or make it what it isn't. This is just what it is. I hope that this platform is helpful. I know there's potentially fewer and fewer people getting on, but hopefully it's helping. So unless somebody's saying something or asking something, I think we're going to call it a wrap for this Q&A session, and we'll pick it up again tomorrow with the new material at 11. So have a good night. Stay safe.